morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here.
This is Andrew and Renee. Welcome to the Stack series.
Today, we are exploring the fundamental architecture of reality, spontaneous symmetry breaking.
It is quite a mouthful when you say it all out loud like that.
It really is, and I have to be completely honest with you. When I first looked at the massive stack of research for today, looking at names like Noether and terms like gauge theory and the sheer mechanics of the Higgs boson, I had this brief moment of just pure panic.
I think we all do when we first see those equations.
Right. I just thought, okay, we're jumping into the absolute deep end of abstract math here. I was seriously ready to call in sick today.
But you're still here.
I'm still here because the more I read through the source material, the more I realized this isn't just about cold, hard math on a chalkboard. It's actually about, well, it's about why we're solid. It's about why things have weight. It is literally the reason that we exist at all.
Exactly. It's the story of how the universe had to essentially break its own perfect rules just to allow us to exist.
And that right there is the hook for me. Because as humans, we tend to associate symmetry with perfection, right? We love symmetry.
Oh, we absolutely crave it.
Yeah, we love it in architecture, think of the Taj Mahal. We love it in human faces. We biologically find symmetrical faces more attractive. We love it in art and design. We just naturally assume that a perfectly symmetrical universe would be the perfect universe.
But the sources we're looking at today show that that's a trap. That's the central paradox we need to grapple with for this whole session.
Because if the universe were actually perfectly symmetrical, it would be a complete wasteland. Nothing would happen. No particles would have mass. Atoms wouldn't be able to stick together. We wouldn't be sitting here recording this, and no one would be out there listening to it.
It would just be this very cold, perfectly beautiful, but incredibly boring place. The entire stack of research we're covering today argues that existence, the messy, heavy, tangible physical reality that you and I live in, is actually the result of a flaw, a broken mirror, so to speak.
I actually wrote down a phrase in the margins of the notes 3 times. Imperfection is the engine of creation.
I like that.
It sounds like something a life coach or a therapist would tell you, but it's literally just particle physics.
It is a very poetic way to view the cosmos. We crave that order, but existence absolutely requires that order to be shattered.
So we have a massive journey ahead of us today. We are going to take our time to really unpack all of this for you. Here is the roadmap for how we're going to tackle this material. We're going to start with the foundations, what we think we currently know. We have to essentially redefine what symmetry actually means to a physicist, because it's not just about butterflies or Rorschach tests.
Right. We'll talk about the actual language of nature, which is group theory, and we absolutely must discuss Noether.
Oh, my personal hero from this research. The woman who proved that conservation laws aren't just these arbitrary traffic rules of the universe. Then we're going to get into the actual mechanics of the Mexican hat potential, which is how the universe broke. And that leads us directly to the Higgs boson and the eating mechanism, which I have to say sounds terrifying.
It's a lot less violent than it sounds, but mathematically it's just as dramatic.
I'll take your word for it. Then we're going to move into the active debate. Because the book on physics is definitely not closed. We have major fundamental disagreements about neutrinos, the ghost particles, and the mathematical nature of the Higgs field itself.
And finally, we will explore the frontiers. We'll look at cosmic inflation, the idea of bubble universes, and the cosmic scars left behind by the Big Bang, which physicists call topological defects.
Which honestly sounds like a weird skin condition, but they are actually literal tears in the fabric of space-time.
Something like that, yeah. And we will wrap up all of this with the implications. Why does any of this matter for things you actually use, like medical imaging or our philosophical understanding of reality itself?
Okay, let's unpack this. Let's start with section 1, foundations. You have to cure me of my everyday definition of symmetry here, because when I hear the word symmetry, I think of folding a piece of paper in half and the ink matches on both sides. Or just looking at a perfect square.
And to be fair, that is a form of symmetry. That's reflectional symmetry. But in physics, when we use that specific word in the source material, we are talking about something much more robust. We are talking about invariance.
Invariance. Okay, define that for me in just plain English.
Invariance just means immunity to change. It means you can do something to an object or to a system or an experiment, and the fundamental result doesn't change. The underlying law remains exactly the same, regardless of the transformation you just applied to it.
Okay, I think I need a concrete example for that.
Sure. Imagine you are doing an experiment on your lab bench. You are measuring how long it takes a metal ball to drop exactly 1 meter. You do the drop, you click the stopwatch, and you get a result, say 0.45 seconds. Now imagine you pick up your entire lab apparatus, you turn it 90 degrees so it's facing the wall instead of the window, and you drop the ball again.
It still takes 0.45 seconds.
Exactly. The result didn't change at all. That means the laws of physics possess rotational symmetry. Gravity doesn't care which way your desk is facing.
But that feels, I don't know, almost too obvious. Like, why would gravity care if I'm looking at a window or a wall?
It feels obvious to us simply because we live in a symmetric universe in that specific regard. But you have to realize what a profound constraint that is on the logic of reality. If the laws of physics did care about direction, if they weren't invariant, the universe would be a chaotic nightmare. You couldn't build a car engine in a factory in Detroit and expect it to actually work when you ship it to Tokyo because the orientation of the engine block relative to the center of the galaxy might be different.
Oh, wow, I see. So symmetry isn't just about things looking pretty or balanced. It's about the consistency and the absolute reliability of natural laws everywhere.
Precisely. It's the bedrock of predictability. And the research breaks this down into 2 distinct flavors. You probably saw the distinction between discrete and continuous symmetries in the notes.
Yeah, I did. Discrete felt a bit like digital, like it happens in steps, and continuous felt more analog, like it was perfectly smooth.
That's a really great heuristic, actually. Think of a snowflake. You can rotate a snowflake and make it look exactly the same, but only if you rotate it by very specific angles, like exactly 60 degrees.
Right, if I rotate it 10 degrees, the points of the snowflake don't line up anymore. It just looks like a crooked snowflake.
So that is a discrete symmetry. It only happens in those specific stepped increments. But now, think of a cue ball from a pool table. A perfect, featureless white sphere.
I can rotate that 1 degree or half a degree or a billionth of a degree.
And it always looks absolutely identical. That is a continuous symmetry. In the language of mathematics, which is called group theory, these continuous symmetries are described by what we call Lie groups. They are smooth manifolds, and these are the ones that physicists really obsess over, because these continuous symmetries are what actually drive the fundamental forces of nature.
Okay, I follow the sphere and the snowflake, but then the stack got a little heavy with this concept of global versus local symmetry. This felt a bit to me like the difference between a totalitarian regime and a local homeowners association.
Well, that's a very unique analogy. Let's try to refine that a bit. A global symmetry is when you change everything, everywhere, all at the exact same time, by the exact same amount. Imagine rotating the entire universe by 5 degrees.
Okay, so everything moves together. Relative to each other, absolutely nothing changes. It's like turning the whole snow globe.
Right. But local symmetry, which physicists call gauge symmetry, is much, much more demanding. It implies that you can change things differently at different points in space and time, and the underlying laws still have to hold true.
So I can rotate my lab bench 5 degrees, and you can rotate your lab bench 10 degrees, and someone on Mars rotates theirs 20 degrees.
And the laws of physics must still work perfectly for all of us.
But wouldn't that just break everything? If I change my coordinate system here and you change your coordinate system over there, how do we ever agree on anything? How does the math not just fall apart?
That is the absolute magic of gauge theory. It turns out that this redundancy, the fact that we can describe the universe with different shifting coordinates at different local points, forces us to introduce something to compensate for those differences. To keep the math working, nature has to introduce force fields.
Wait. Are you saying that forces, like electromagnetism or gravity, exist because of this local coordinate problem?
Essentially, yes. The interaction, the force field itself, is the price the universe pays to maintain that local symmetry. It's like the universe saying, you can change the labels locally however you want, but only if you introduce a photon into the math to balance the books and keep everything invariant.
That is completely wild. So forces aren't just these invisible ropes or things that float around in space. They are literally geometric consequences of the universe demanding symmetry.
Exactly. They fall out of the math as a requirement. But before we get to the breaking of these symmetries, we have to talk about why we care about them at all in the first place. And that brings us to the woman who finally connected all these dots, Noether.
I went down such a rabbit hole on her while reading the sources. We're talking 1918, Germany. She's fighting just to be allowed to teach at a university because she's a woman. She actually had to lecture under a male colleague's name for a while just to get into the room. And meanwhile, she just casually drops a mathematical theorem that solves a massive problem that even Einstein couldn't figure out.
It is genuinely one of the greatest intellectual feats of the 20th century. Before Noether, we had these conservation laws. We knew energy was conserved. We knew momentum was conserved. But we just treated them like empirical facts, just arbitrary rules we noticed, kind of like saying what goes up must come down.
We knew they existed, but we didn't know why.
Right. Noether looked at the very deep math and proved something startling. She proved that every single continuous symmetry in nature mathematically creates a corresponding conservation law. They aren't separate concepts. They're literally two sides of the exact same coin.
So let's run through the big ones from the source material, because this really cements the idea for me. You mentioned time translation symmetry earlier, the idea that the laws of physics don't change from Tuesday to Wednesday.
Right. If the laws of physics are invariant under time translation, Noah proves mathematically that energy must be conserved, period.
And that makes total sense when you think about it. If the laws changed tomorrow, like, if gravity suddenly got twice as strong on Wednesday, I could lift a heavy weight today while it's relatively light, wait for Wednesday when gravity gets stronger, and let it drop to generate massive amounts of power. I'd be creating free energy out of nowhere just by waiting.
Exactly. Perpetual motion machines and free energy are fundamentally impossible simply because time is symmetric. The rules don't change over time.
And what about spatial symmetry?
If the laws of physics are the exact same here in this room and on Mars, which is spatial translation symmetry, then Noether showed that momentum must be conserved.
And rotation, the lab bench analogy.
If space has no preferred direction rotational symmetry, then angular momentum is conserved. That's why a figure skater spins much faster when they pull their arms in. It's not just a neat trick. It's a direct, unavoidable consequence of the geometry of space itself.
It is just so elegant. It connects the pure abstract logic of the universe directly to the hard numbers we actually measure in a laboratory. It proves that conservation laws aren't just arbitrary traffic rules the universe decided to blindly enforce. They are unavoidable consequences of the shape of the universe's logic.
It shows that the universe has a profoundly coherent structure at its base. But, and here's where it gets really interesting for today's topic.
The plot twist.
The plot twist. We look around the universe today and we see a world that is incredibly messy. It is full of distinct stuff. We have particles with wildly different masses. We have different forces with totally different strengths. Electromagnetism is vastly stronger than gravity, for instance. If the underlying math is so beautifully, perfectly symmetric, why does the world look so completely broken and varied?
And that is the cue for spontaneous symmetry breaking, or SSB.
Yes. The key conceptual distinction here in the material is that the underlying laws of physics can be perfectly symmetric, but the state of the system itself, specifically what we call the ground state or the vacuum, might not be symmetric at all.
I found a couple of really great analogies in the research stacks to visualize this. One is the ferromagnet, which feels very, high school physics class. But the other is the dinner party, which honestly just triggers my social anxiety.
Let's do the dinner party. It's a classic way to explain it. It's basically the Buridan's ass paradox of etiquette.
So paint the picture for us. We're sitting at a round table, perfectly round.
Perfectly symmetric. You have guests seated all around this large table, and exactly halfway between each plate, there is a neatly folded napkin.
So I'm sitting there, and I'm looking at the napkin to my left and the napkin to my right. They are exactly equidistant from my plate. There is absolutely no geometric or logical reason to pick one over the other.
The symmetry is absolute perfection. The laws of the dinner table treat left and right equally. But in order to eat your meal, you must choose a napkin.
The tension is building. I'm hungry. I finally just reach out and grab the napkin on my right.
Symmetry broken.
And here's the kicker of the analogy. Because I took the napkin on the right, the person to my right now has to take the napkin to their right because I just stole their left one.
It creates an instant cascade. Instantly, the entire table shifts from a perfectly symmetric, undecided state to a strictly right-handed state. Everyone is using the right napkin.
But notice this, and I think this is the crucial part the sources emphasize. The table itself didn't change. The plates didn't physically move. The rules of the dinner party remained totally symmetric. I could have just as easily picked the left napkin, but the final outcome was entirely asymmetric.
That is the pure essence of spontaneous symmetry breaking. The underlying equations and laws remain symmetric, but the physical system falls into a ground state that is fundamentally not symmetric. It essentially chooses a path.
Now, how do we actually translate napkins and dinner plates into particle physics? Because the sources bring up a very famous shape to explain this mathematically. The Mexican hat potential.
Right, or sometimes it's described as the bottom of a wine bottle. Visualizing this shape is really key to understanding the mass of the universe. Imagine a graph of potential energy. Usually when we think of a stable physical system, we just picture a simple bowl. You put a marble in a bowl, it rolls down at the bottom right to the center. That center is the lowest energy state.
And that center point is completely symmetric. It's exactly in the middle.
Correct. But now, I want you to imagine that the bottom of this bowl actually has a hump right in the middle, like a sombrero. The very center of the bowl is actually a peak.
So if I try to put the marble exactly in the center, it's basically balancing on top of a steep hill.
That is technically an equilibrium point, but it is highly unstable. At the top of that peak, it is perfectly symmetric. It looks exactly the same down all sides. But the slightest nudge, even a tiny random quantum fluctuation, will cause that marble to roll down the side of the hump.
And where does it roll to? It rolled down into the brim of the hat, the circular valley at the bottom.
Exactly. That valley is a continuous circle surrounding the central peak. The marble can land absolutely anywhere in that circular valley. But it must land somewhere. And once it randomly lands at a specific point, let's say it lands at the north position of the valley, the symmetry is instantly broken. It has chosen a specific value.
Now, this leads to a very specific and massive problem in the physics history we are looking at called Goldstone's theorem.
This is a major hurdle in the 1960s. When you break a continuous global symmetry like that marble rolling down into the brim of the hat, the mathematics strictly predicts the creation of new massless particles. We call them Nambu-Goldstone bosons.
And just to clarify, this is because moving around the brim of the hat, like rolling the marble in a circle along the flat bottom of the valley, costs zero extra energy, right?
Yeah.
The valley floor is perfectly flat.
It's exactly right. In quantum field theory, an excitation or movement that caused zero energy corresponds directly to a massless particle. But here was the massive crisis for physicists. We didn't see these massless particles anywhere in nature. There are no weightless ghost particles floating around everywhere. And when we looked at the weak nuclear force, we actually saw the exact opposite problem. We saw gauge bosons, the W and Z particles, that were incredibly heavy.
So the prevailing theory predicted all these weightless ghosts, but physical reality gave us heavyweights. That seems like a pretty fatal flaw for the theory.
It really seemed that way. It kept theoretical physicists up at night for years, until Peter Higgs, Francois Englert, and a few others realized something truly profound. When you apply this symmetry breaking not to a global symmetry, but to a local gauge symmetry, something entirely magical happens to those theoretical Goldstone bosons.
The Higgs mechanism, or as I like to refer to it in my notes, the Pac-Man mechanism.
The eating mechanism, yes.
Okay, you have to explain this eating concept, because usually in physics, particles don't just eat each other like a video game.
Well, in the standard model, we postulate that the Higgs field pervades all of empty space, everywhere, and it has that exact Mexican hat potential we just talked about. When the early universe cooled down after the Big Bang, the Higgs field rolled down from that center peak into the valley. Essentially, the field turned on.
Okay, I'm with you. The field is on.
Now, usually, as we said, this rolling down would create those problematic massless Goldstone bosons. But because this Higgs field is constantly interacting with the gauge field, specifically the fields of the weak nuclear force, those Goldstone bosons don't actually get to become physical independent particles. Instead, they're literally eaten by the W and Z gauge bosons.
So the W and Z particles just swallow these mathematical ghosts whole.
Essentially, yes. They absorb those mathematical degrees of freedom, and by swallowing them, they gain what we call a longitudinal polarization. But in plain English, it means they get heavy, they gain mass.
So the problematic ghosts disappear entirely, and the W and Z particles get fat. Two massive physics problems solved with one single mechanism.
Precisely. The gauge bosons become very short-ranged and very heavy, which is exactly what we observe in experimental nuclear physics.
But wait, what about the photon, the particle of light? It somehow escaped this cosmic feast.
The photon is the sole survivor of that sector. The symmetry breaking was very specific. It broke the electroweak symmetry, but the way it aligned left the pure electromagnetic symmetry completely intact. The vacuum of space remained electrically neutral, and because of that, the photon remains perfectly massless.
So, just to make sure I really grasp this, mass isn't just an inherent amount of stuff packed into a particle. Mass is actually a measure of how much a particle is dragging its feet through this invisible Higgs field.
That is the standard and probably most accurate analogy. Think of the Higgs field like a large room completely packed full of people at a cocktail party.
We're going to a lot of parties in physics today.
It's a very social science. Imagine a highly famous celebrity walks into this crowded room. Let's say Einstein walks in. Immediately, everyone crowds around him to talk. It becomes very hard for him to move across the room. He's experiencing high inertia. In particle terms, he has high mass. That's exactly what the top quark experiences. It interacts strongly with the field.
And if I walk into the party, I'm a total nobody.
You can walk right through the room to the bar. Almost no one stops you or interacts with you. You have very low mass. That is like an electron.
And a photon.
A photon is like a ghost at the party. It passes through the entire crowd without interacting with a single person. It experiences zero resistance, so it has exactly zero mass. It travels at the speed of light.
That is incredible. So we aren't just swimming in empty dead space. We're constantly moving through a dense condensate, like a cosmic molasses that particles are constantly bumping against, and that exact resistance is what we perceive as mass.
Precisely. Without this specific symmetry breaking mechanism, electrons would be entirely massless. They would just fly about randomly at the speed of light. Atoms could not hold on to them. Chemistry would be absolutely impossible. Life, planets, stars, all of it would be impossible.
It really is the fundamental architecture of existence. But Renee, looking at the stack of papers here, it seems like the standard model isn't the final word on this. As tidy as the cocktail party sounds, there are some pretty major cracks in this mirror.
There are very significant cracks. Which brings us naturally to our second section, active debate. Where does the scientific community actually disagree right now?
The first big one that jumped out at me from the sources is neutrinos.
Ah, yes. The ghost particles.
Because for a really long time, the standard model just assumed neutrinos were perfectly massless. They were just these tiny, neutral little things that zipped around near the speed of light and barely interacted with anything.
That was the standard assumption for decades. But then we discovered a phenomenon called neutrino oscillation. We realized through massive experiments that neutrinos can actually change their flavor. An electron neutrino can literally turn into a muon neutrino as it travels through space. Now, relativity tells us this is only possible if the particle experiences the passage of time. And a particle can only experience time if it travels slower than light, which mathematically means it absolutely must have mass.
But wait, the standard Higgs mechanism we literally just talked about, the cocktail party, does that explain where this neutrino mass comes from?
It can explain it, but it is extremely awkward. This is the root of the massive debate between Dirac neutrinos and Majorana neutrinos.
Okay, let's break that down for the listener. Dirac neutrinos are what we would consider the normal ones.
Right. Dirac neutrinos would get their mass exactly like the quarks or the electrons do. You would simply write down a mathematical coupling to the Higgs field in the equations. But there's a glaring problem with doing that. We know from experiments that neutrinos are unimaginably light. We are talking millions of times lighter than even the electron.
So the coupling number, the measure of how popular they are at the cocktail party, would have to be absurdly tiny, like 0.0000000000001.
Exactly. It feels incredibly unnatural to a physicist. Physicists despise unexplained, arbitrarily tiny numbers in their equations. Why would this one specific coupling be so vastly smaller than all the others? This deep discomfort leads many physicists to suspect a completely different mechanism is at play, the Majorana mass.
And Majorana means the particle is actually its own antiparticle.
Yes, which sounds impossible if you think about a charged particle. An electron cannot be its own antiparticle because its antiparticle, the positron, has a positive charge, but a neutrino is electrically neutral. It has no charge to flip.
So if a neutrino touches another neutrino,
if they are truly Majorana particles, they could theoretically annihilate each other. This property allows for a completely new kind of mass term in the math, and it leads to what physicists call the famous seesaw mechanism.
I genuinely love the visual of this from the sources. A literal playground seesaw.
Imagine a seesaw. On one side, you have a hypothetical, incredibly heavy particle, a right-handed neutrino that is extremely massive. We're talking maybe as heavy as an entire galaxy, relatively speaking, in the particle world. Because it is so extraordinarily heavy, it pushes its side of the seesaw all the way down into the dirt.
And naturally, the other side shoots way up.
Right. The other side of the seesaw is the standard left-handed neutrino that we actually observe in the lab. Because its theoretical partner is so enormously heavy, our everyday neutrino is mathematically forced to be incredibly, almost vanishingly light.
So instead of needing a tiny, weird, unexplained number in the math, we just need a massive, heavy partner particle that we simply haven't built a big enough collider to find yet.
Exactly. It explains the tiny mass perfectly naturally. But there's a catch. If this seesaw theory is true, it implies that lepton number, which is a strictly conserved quantity in the Standard Model, is actually broken. It means the fundamental divide between matter and antimatter is much more mixed and fluid than we ever thought.
And how do we actually test something like that? We can't just build a galaxy-sized collider.
We look for a very specific event called neutrinoless double beta decay. It's an incredibly rare type of radioactive decay that can mathematically only happen if the neutrino is its own antiparticle. We have deep underground detectors looking for it right now. If we see even one event, it quite literally rewrites the physics textbooks overnight.
Speaking of rewriting textbooks, I saw some incredibly dense papers in the stack about HFT versus MFT, and honestly, it sounds like a professional boxing match. In the red corner, we have AFT.
It basically is a boxing match, but it's a battle of effective field theories. It's fundamentally a debate about the resolution of our microscopic view of the universe.
Explain that resolution analogy a bit more.
Sure. The Standard Model effective field theory, or SART, assumes that the Higgs boson is a fundamental, indivisible particle, a single point, like a single pixel on a screen. It assumes that any new physics we find will just be small, linear mathematical corrections on top of this perfect little point.
And AFT assumes something different.
Higgs effective field theory, or HFT, is a much more generalized approach. It asks a radical question. What if the Higgs is not a fundamental point? What if we zoomed in close enough with a powerful enough collider, we saw that it was actually a fuzzy blob? What if it's a composite state made of smaller, unknown things tightly bound together?
Oh, like how we used to think a proton was a solid point, but then we zoomed in and realized it's actually a bag of 3 quarks.
Exactly the same concept. If the Higgs is composite, the underlying geometry of the math changes completely. We have to use advanced mathematical tools, things like the Hilbert series, to count the possible mathematical operators and try to distinguish between these two scenarios. It turns out, depending on which theory is actually correct, the Higgs will interact with highly energetic particles in very, very different ways.
And this composite idea ties back into the naturalness problem, right? The question of why the Higgs is so remarkably light to begin with.
Yes, the infamous hierarchy problem. Think about it. If the Higgs field gives mass to absolutely everything, it means it interacts with absolutely everything. Quantum mechanics dictates that the energy from all those constant interactions should mathematically add up. The Higgs mass should theoretically be enormous. It should be driven all the way up near the Planck scale.
But it's definitely not. We measured it at CERN. It's about 125 gigaelectron volts. It's incredibly light.
It's basically like finding a single bird feather that weighs exactly as much as a feather, even though you know it's been soaked in dense lead paint. It defies the baseline logic. It strongly suggests there must be some hidden mechanism, some undiscovered symmetry, that is actively protecting the Higgs mass and keeping it small. For decades, we thought that protector was supersymmetry. But we've run the Large Hadron Collider for years, and we haven't found a single partner particle yet.
So the mirror of the Standard Model is definitely cracked, but we haven't quite found the new glass to replace it yet.
Not yet. But let's zoom out for a minute. We've been talking intensely about the tiniest subatomic particles. Let's shift gears and talk about the universe itself on the grandest scales. Section 3 of our exploration, Frontiers.
This is where things get truly cinematic in the research, cosmic inflation.
If you thought the Higgs mechanism was an impressive piece of symmetry breaking, inflation takes that exact same mathematical concept and applies it to a cosmic scale. The core idea is that in the very, very early universe, fractions of a fraction of a second after the initial Big Bang, a scalar field, which we often call the inflaton field, rolled down a potential energy curve that looks extremely similar to the Mexican hat of the Higgs.
And this rolling down caused the literal fabric of the universe to expand exponentially, faster than the speed of light.
Much faster. It stretched the very fabric of space out. It took a region of space smaller than a single atom and violently stretched it to the size of a galaxy in a fraction of a heartbeat. And this connects directly back to our symmetry-breaking theme through the mind-bending idea of bubble universes.
Yes, the false vacuum scenario. I was reading this late at night, and this is quite literally the stuff of existential nightmares.
It is incredibly dramatic physics. Imagine the early universe is sitting quietly in a local valley of potential energy. It seems perfectly stable. We call this a false vacuum state. But imagine there was actually a deeper, lower valley, a true lowest energy state, further away, separated by a high mountain range of energy.
It's like being in a pristine, calm lake high up in the mountains. It feels like you're at the lowest point, but if you could somehow tunnel straight down through the solid rock, you'd drop thousands of feet down to actual sea level.
Exactly. And quantum mechanics allows for exactly that kind of tunneling.
Hmm.
Randomly, bubbles of the true vacuum can nucleate and form within the false vacuum. And once a bubble forms, its walls expand outward at the exact speed of light, destroying the old vacuum. Inside that new bubble, the laws of physics might look completely different because the symmetry is broken in a totally different way.
The source from Oregon had a genuinely fantastic analogy for visualizing this using the art of M.C. Escher.
Yes, the heaven and hell print. Have you seen that one?
I have. It's the circular woodcut where the angels and the devils fit together perfectly like puzzle pieces. But as you look toward the outer edge of the circle, they get infinitely smaller and smaller.
Right. That specific piece of art is actually a perfect 2D representation of hyperbolic space. In the context of these cosmic bubbles, it represents the bizarre reality of having an infinite space contained entirely inside a finite boundary.
Wait, you need to run that by me again. Infinite on the inside, but finite on the outside. How does that work?
It's entirely due to the negative curvature of space-time inside the true vacuum bubble. If you were watching from the outside in the false vacuum, the bubble just looks like a finite expanding sphere. But if you were actually living inside the bubble, space would stretch out and warp in such a way that it goes on forever. You could get in a spaceship and travel for 1,000,000,000,000 years and you would never hit the bubble wall.
That is just mind-bending geometry, purely Escher-esque.
It is. And inflation isn't just a cool, trippy sci-fi story. It actually mathematically solves some of the most stubborn headaches for modern cosmologists. For instance, it solves the horizon problem. The mystery of why the cosmic microwave background temperature is exactly the same everywhere we look in the sky, even in regions completely disconnected from each other.
Because thanks to inflation, they actually were physically connected in a tiny speck right before it blew up and stretched out.
Exactly. And it solves the flatness problem, the mystery of why the universe's geometry appears perfectly flat on a large scale. Inflation violently stretched it all out, kind of like ironing a massively wrinkled shirt until it was flawlessly smooth.
But, and this is a big but in the research, when you iron a shirt or when you freeze water into a block of ice, you inevitably get defects. You get wrinkles or you get cracks.
Yes, topological defects. These are the literal scars of the Big Bang. This phenomenon is known as the Kibble mechanism.
Imagine a large lake freezing over in the winter. It doesn't all freeze uniformly at once. It freezes in separate patches all over the surface.
Correct. You have these isolated domains of ice forming independently. In one domain, the molecular crystal lattice of the ice aligns perfectly to the north. In another patch nearby, it happens to align to the west. When those two growing domains eventually expand and crash into each other, their internal orientations cannot match up perfectly. You inevitably get a visible crack, a defect in the ice.
So, in the early universe, as the cosmic symmetries broke, different regions of space essentially chose different directions for the symmetry breaking. And when those expanding regions met, they trapped immense amounts of energy in the mismatch.
Exactly. And depending on the specific mathematical type of symmetry that was broken, you get very different, very exotic types of physical defects.
The sources outline a few. We have domain walls, for instance.
Right. Domain walls are basically massive 2D sheets of concentrated energy spanning across the universe. But they're highly problematic. If they existed, they would be so disastrously heavy that their gravity would dominate the mass of the entire universe and crush it. We obviously don't see them, so cosmologists assumed that inflation pushed any walls far, far away, well outside our observable horizon.
Then we have monopoles, zero-dimensional point defects.
Isolated north or isolated south magnetic poles. Grand unified theories strongly predict that they must be created. But again, we look out and we don't see them anywhere. The monopole problem was actually one of the primary historical motivations for inventing inflation theory in the first place. Alan Guth realized inflation would dilute them so drastically that maybe there is only one single monopole left in our entire observable universe.
Just imagine being the experimentalist who actually finds that one monopole. It would be the holy grail of physics. But moving on, we have the most intriguing defect of all mentioned in the stack, cosmic strings.
Ah, yes. One-dimensional lines of pure trapped energy. They are infinitely long, thinner than a single proton, but unbelievably, unimaginably dense. A single kilometer of a cosmic string could weigh as much as the entire planet Earth.
And the sources mention some genuinely wild variations of these strings, like superconducting strings.
Yes, the brilliant physicist Edward Witten showed mathematically that under certain vacuum conditions, these strings could act as perfect superconductors, carrying massive, universe-spanning electrical currents. And if you happen to get a closed loop of such a superconducting string, it becomes something called a vorton.
A Vorton. I have to say, that sounds exactly like a comic book villain.
It does, but physically, it is a stable, perfectly closed loop of string. It's essentially an eternal knot of energy that mathematically cannot untie itself. Some exotic theories even suggest these vortons could be a viable candidate for dark matter. They are incredibly heavy, they don't interact much with normal light, and they were ancient leftovers from the very beginning of time.
But how do we actually hunt for these cosmic scars? We can't exactly go looking for a microscopic string with a telescope.
We can't see the string itself, but we look for its massive gravitational effects. A cosmic string is so heavy, it would act as a profound gravitational lens. If a string passed directly between us and a distant galaxy, it would warp the light so severely that we might see a perfectly identical duplicate image of that galaxy sitting right next to it.
Or we look for the Kaiser-Stebbins effect on the cosmic microwave background, right?
Right. Think of the CMB as an incredibly detailed map of the universe's background temperature. If a cosmic string moves laterally across the sky, its gravity creates a sharp step function, a literal sudden jump in temperature across a distinct line.
Okay.
One side of the string's path looks instantly hotter and the other side looks instantly cooler.
And we are also actively listening for them with gravitational wave detectors like LEGO, aren't we?
Yes, we are. Because a massive loop of cosmic string wouldn't just sit there. It would violently oscillate at near the speed of light, slowly radiating away energy and decaying. That decay should produce a stochastic background. Basically, a constant low-level hum of gravitational noise. We're literally listening to the fabric of the universe to hear if it's humming with the sound of snapping cosmic strings.
Which is just a breathtaking endeavor. And that brings us to the biggest, most ambitious symmetry of all, grand unification, or GUTs.
The ultimate dream of physics, the unification of the forces. We deeply believe that at unimaginably high energies, like those right at the Big Bang, the strong nuclear force, the weak nuclear force, and electromagnetism were not separate. They were all merged into one single elegant master force.
The Trinity became one.
Exactly.
Hmm.
We try to model this master symmetry with massive mathematical groups like SU5 or SO10.
And as the universe expanded and cooled, this pristine master symmetry shattered.
It shattered in distinct stages. First, we think gravity broke off from the master force at the Planck era. Then, as it cooled further, the strong force separated from the electroweak force. And finally, the Higgs mechanism we talked about broke the electroweak into the everyday forces we see now.
But if they were genuinely all the same force at one point, the sources say there should be a lingering bridge between them. Quarks should theoretically be able to transform into leptons.
Which leads to the most staggering prediction of GUTs, proton decay. If this master symmetry allows quarks to change flavor so drastically, then diamonds are truly not forever. Protons, the fundamental stable building blocks of all everyday matter, should eventually decay into lighter particles like positrons and pions. The very matter you are made of is fundamentally unstable.
But wait, we haven't actually seen a single proton die yet, have we?
No, we haven't. We have built these massive cathedral-sized tanks of ultra-pure water deep underground in abandoned mines, like the Super Kamiokande detector in Japan, and lined them with thousands of light sensors, just patiently watching for a single proton in the water to blink out of existence. We've been watching continuously for decades, and so far, absolutely nothing.
Which has to be frustrating, but it also puts a hard limit on the theory, doesn't it?
It does. The silence tells us that if protons do decay, their half-life must be incredibly long, at least 10 to the 34 years. That is billions and billions of times longer than the current age of the universe. It just continually pushes the frontier of our experiments further and further out.
It's just amazing to me how these highly abstract symmetries on a chalkboard dictate the literal lifespan of physical matter itself. Which brings us to our final section, implications. Why does any of this deep, dense physics actually matter to the listener in their daily life or to society as a whole?
Well, aside from the profound existential question of why we have mass and why we exist, there are direct technological analogies that are very, very real. We briefly touched on superconductors earlier.
The lab bench universe, as the notes called it.
Superconductivity is essentially the exact non-relativistic equivalent of the Higgs mechanism, but happening right here on Earth. In a supercooled material, photons actually gain mass.
Wait, hold on. Light gets heavy.
Inside that specific material, yes, it does. Because the photon becomes heavy and sluggish, the magnetic field it carries cannot penetrate deep into the superconductor. It gets expelled. This is called the Meissner effect. And the mathematical description of this expulsion is exactly, perfectly identical to the equations of the W and Z bosons gaining mass in the early universe.
And we use this exact effect every day. MRI machines in hospitals, maglev trains floating above the tracks, squiddies used in precision engineering.
Exactly. The advanced medical imaging that saves millions of lives relies fundamentally on the physics of symmetry breaking. Understanding these abstract phase transitions in the early universe directly helps us engineer miraculous materials right here on Earth. It's all connected.
But beyond the technology, there's also a deep philosophical layer to this stack that I really resonated with. The idea that mass is interaction.
It requires a massive shift in how you view reality. We are trained to think of mass as just stuff. Inertia. A solid rock is heavy because it's a rock, and it's full of rock stuff. But symmetry breaking teaches us that mass is actually a relationship. It is purely a measure of how you interact with the invisible background field of the universe.
We only exist as solid beings because we interact. If our particles didn't interact with the Higgs field, we wouldn't be solid. We would just be ghosts of light. We literally wouldn't be us.
And it highlights the absolute necessity of imperfection. If the universe somehow managed to stay in that beautiful, perfect, highly symmetric energy state, it would be forever cold, totally empty, and perfectly uniform.
Broken symmetry is the engine of complexity.
Life itself completely relies on the frozen accidents of the early universe. The specific random values of the particle masses. The specific random ways the symmetries broke as the cosmic temperature dropped. We are, quite literally, the children of a broken mirror.
That is just such a beautifully poetic way to put it. And there is one more philosophical nugget from the gauge theory section that I wanted to bring up. Redundancy versus reality.
Ah, yes. We said much earlier that gauge symmetry is fundamentally a mathematical redundancy in our description of the universe. It forces us to ask a deeply uncomfortable question. Are the force fields we feel actually real? Or are only the invariants, the underlying things that never change, the actual reality?
Right, because in a relativistic universe where everyone has different relative viewpoints and coordinate systems, those absolute invariants are the only true objective facts.
It strongly suggests that our everyday perception of physical forces, like feeling a magnet pull on iron, might just be the result of our local perspective trying to maintain a consistent mathematical description of reality across space and time. The force is just an accounting trick of nature.
And that connects directly to the Aharonov-Bohm effect mentioned in the final pages, right? Where invisible potentials seem to have real measurable effects on particles, even when the actual force fields are zero.
Yes. In that experiment, you could shoot an electron past a shielded solenoid where the actual magnetic field is strictly zero. But the electron still somehow feels the underlying potential. It shifts its quantum phase. It strongly hints that the so-called redundant potentials in our math might actually be more fundamentally real than the tangible forces we measure with our instruments. It is an incredibly deep rabbit hole.
A rabbit hole we will absolutely have to save for another session, I think. But it really just makes you question what reality actually is at its core. Is it the solid particle? Is it the invisible field? Or is it just the pure math underneath it all?
I think the only honest answer we have right now is reality is the symmetry itself and the beautiful, chaotic breaking of it. And maybe, just maybe, the laws of physics themselves are still slowly evolving today as part of some ultimate ongoing symmetry-breaking event we can't even perceive yet.
Now that is a thought to leave everyone with. Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. We hope you enjoyed today's discussion. If you did, be sure to subscribe and support us in Patreon. And of course, you can write to us in comments if a specific topic needed to be covered, which help us all to grow.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.